Let us define Cauchy sequence. If xn is a Cauchy sequence, then we have mod of xn plus p minus xn less than epsilon for all p positive integer and a large n. So we have, after this threshold value, all the values of xn coming closer to each other. If we write the values of this sequence xn as this, we easily see that even the difference between xm plus p and xm is also arbitrarily small. Remember that epsilon is a arbitrarily small positive integer. So all these terms are getting closer to each other. So this is the definition of Cauchy sequence, and from this definition it naturally follows that if xn is a convergent sequence which converges to a specific limit L, then we have mod of xn minus L less than epsilon for all n greater than, say, a threshold value m prime. So mod of xn plus p minus xn may be written as mod of xn plus p minus L plus L minus xn, which is less than mod of xn plus p minus L plus mod of xn minus L. And since mod of xn minus L is less than epsilon for all n greater than m prime, so n plus p is also greater than m prime, since p is positive. So both these terms are less than arbitrary small number. We choose them to be epsilon by 2, so that this is less than epsilon. So we have proved that any convergent sequence is a Cauchy sequence. It can also be shown that if we have a Cauchy sequence, it will be always convergent. How? Since if xn is a Cauchy sequence, then mod of xn plus p minus xn less than epsilon for all p positive integer as well as n greater than a threshold value capital M shows that this sequence is bounded. From this condition we can easily infer that this is bounded, simply because for all the values of n greater than m we have mod of xn less than a bounded value, and for all the values of n less than m we have finite number of xn's, x1, x2, x3 dot dot xn minus 1, and we can always choose the greatest value among this to be capital K, so that we may write that mod xn is less than k for all n. Okay, so this sequence, Cauchy sequence, is always bounded, and we can apply Bolzano-Weierstrass theorem to find a subsequence of this mother sequence. We can always apply Bolzano-Weierstrass theorem to find a subsequence of this which is convergent to a specific limit L. We intend to show that this sequence is also convergent to this L. This can easily be established if we write mod of xn minus L as xn minus xn plus p plus xn plus p minus L, and denote by this x and k all these values of xn plus p. Obviously xn plus p is a subsequence of this sequence, and Bolzano-Weierstrass theorem states that this subsequence is convergent to L. So this can easily be, this is less than epsilon and this is less than epsilon. So we can easily see that epsilon prime is another small arbitrary number, positive, which is ensuring that the sequence is convergent. Hence, we see that this is a necessary and sufficient condition, or if and only if condition, that a sequence is convergent if and only if it is a Cauchy sequence. It is both ways. Whenever a sequence is a Cauchy sequence, it is convergent, and whenever it is convergent, it is a Cauchy sequence. It is a very strong result, and we shall apply this result to see that a very interesting sequence written as sum over 1 by n equal to 1 to n, which is termed as harmonic series, is this sequence is not a Cauchy sequence. And since it is not a Cauchy sequence, we can easily infer that this is a divergent sequence. So what is this sequence? This sequence is 1, then 1 plus half, then 1 plus half plus 1/3, and so on, with the nth term as this. Isn't it so? And it goes on. And we shall show that this is not a Cauchy sequence. Let us just calculate with this definition the value xn plus p minus xn, mod of xn plus p minus xn. So it will be mod of 1 plus half plus 1/3 plus 1 by n plus 1 by n plus p minus 1 minus half minus 1/3 minus 1 by n. So obviously all these terms cancels out, and we have here starting from 1 by n plus 1, then 1 by n plus 2 up to 1 by n plus p. Okay, since all these terms are positive, n is natural number, p is positive, it is given, so all these terms are positive. We don't need to keep this mod. And now we just remember that since p is positive, n plus p is always greater than n, or we may say that 1 by n is always greater than 1 by n plus p. So we replace each and every term by 1 by n plus p. So it is greater than p by n plus p. There are p number of terms, and we replace each term by n plus 1 by n plus. So each and every term is greater than that. Okay, we may write it as this. P is integer, we may put a equal to sign also. And now we see that since p is any integer, if we choose p to be equal to n by 2, we can easily choose p to be n by 2, then this becomes 1/3. If we choose p equal to n, then it becomes half. Isn't it so? So we can easily infer that mod of xn plus p minus mod of xn is not less than epsilon for any arbitrary small positive number, because it is greater than half or greater than 1/3, which are finite quantities. Hence we claim that the sequence summation 1 by n harmonic series n equal to 1 to n is not a Cauchy sequence, and hence it is divergent. Okay, because Whenever it is a Cauchy sequence, it is convergent, and whenever it is convergent, it is Cauchy sequence. So whenever it is not a Cauchy sequence, it cannot be convergent.